Well, listen, I'm going to get things kicked off. So, my name's Jake Kitchener. I've been working on Kubernetes and OpenShift platforms since, I guess, late 2016 now, and I've had a lot of experience from public cloud to now working at Fidelity Investments and working on our cloud platform there. And I guess, I'm very passionate about Kubernetes, you know, building and running Kubernetes applications and processes in production. I'm always happy to share an opportunity to take the opportunity to share a little bit more about, my experience with Kube, and some of the learnings that I've gathered over the years of building and running Kubernetes clusters and applications over the years. One thing I will say is that it's not all shiny happy. Look, you definitely go through some fires when you're going through the process, especially in the early days. I think, back in late 2016 and early 2017, when I was first getting started on the Kubernetes platform, there was a lot of unknowns. We hadn't learned that many lessons yet. Kubernetes was definitely a very different beast of maturity than it is today. I'm happy to report that I think, today we certainly are consistently achieving all of our availability goals when it comes to our Kubernetes clusters, and our applications that we're running on it. And hopefully, some of the data and information I can share today will help others achieve that same in their future as well. So I want to start and talk a little bit about availability, right? Like, I think, for those of us that are running applications and services in production, availability is very much one of the main things that is driving, our success and our ratings as far as, our success in our career and for our companies. I think it's important to understand some of the fundamentals. We often talk about like uptime and MTBF and MTTR and all these things. And I think it's helpful to kind of understand, like, what is the impact of these letters, numbers, et cetera. And like the key is that at the end of the day, most folks, there's some expectation from their boss or their boss's boss or their boss's boss's boss, whoever it is, about, what is the availability of your applications and services. And, often we talk about this in like how many nines are we able to achieve for our applications. And I think it's interesting to take a look at like, well, what does it take to actually get to those numbers, right? And so, we'll talk about things like 99% uptime, or 4 nines is 99.99% up, right? And if you do the math on those numbers, assuming like 720 hours in a month, this is how much downtime you can have, right? So if you're at 99%, you get 7 hours of downtime a month, which is, in the grand scheme of things, quite a bit. That certainly leaves plenty of room for humans to be on the job and repairing systems and things like that, assuming you don't have very many incidents. But when you get into the 4 nines territory, that means that whatever application or service it is that you offer, you get 4 minutes and 22 seconds of downtime a month. And, that's not a lot. And that's not an uncommon expectation for the availability of a service or application, right? So, well, how do we figure out? I mean, this is just kind of like a random, like, what does it mean to be down? How do we get to those availability numbers? And, on the right-hand side here, we talk about mean time between failures and mean time to recover. And this is like, for those that are in SRE or operations or DevOps, right? Like, these things should be near and dear to everybody's heart. And it's really important to kind of understand how those things work together, right? So mean time between failures, just how often does it break? And mean time to recover is how long does it take to fix it? And I think it's interesting to look at this, right? So like, let's assume that our boss is very reasonable and only expects 99% availability, right? And, at that 99% availability, if you experience some kind of failure, once a day, that means that in order to hit that number, you can only spend 14 minutes per failure to recover before you're going to break, your budget. Now, remember, like, that's at 99%. Now, if we went and did the math, right, and you're trying to get to 4 nines, and if you had a failure once a day, that means you get something like 17 seconds per failure to recover from those things to be able to hit your targets. And as you would guess, right, like the math doesn't look pretty good. Now, here's the really fun thing is that, you know, if the availability of the system or the application or service needs to be two nines, for example, in this simple case, but you've got a huge complex system, right, that consists of, I don't know, hundreds of applications running across a huge fleet of servers and stuff like that. If you're experiencing failures on individual servers, right now, like a great example is Amazon. I think their expectation is something like 7 or 8 hours of downtime for each VM every month. So, if you had a couple hundred VMs, you should expect a couple of those to fail on a daily basis based on like Amazon's, quoted availability. Now, they regularly achieve way better than that for an individual VM, but like that's kind of what they guarantee for one VM in one availability zone. So, as you can tell, right, like in a big complex system, you're going to be experiencing failures constantly within that system. And you need to be able to deal with those, in an automated fashion, or in a way where it has zero impact on the availability of the system. And so, it's nice to think about, well, how do we go from availability to what we often hear of as high availability, or HA, right? And to get there, right, we introduce components into our system that prevent us from having to like perfectly manage each and every single server that's part of the larger system. And if you can get to that point where, let's say one of your three servers in this example fails behind the load balancer, well, guess what, right? Like you're not going to have any downtime as a result of that, because the load balancer can perform retries and do health checking and things like this, so that, the client at the top there doesn't actually see that there's a failure of one of those servers. Now, we're cheating a little bit here, right? That load balancer that we have pictured here in the middle, somebody's got to manage the availability of that thing and make sure that it achieves some uptime. But like, especially if we're talking in cloud, then there's a lot of managed services that are available to us where, the load balancers can get to 4 nines or better with no effort on our part. So this is where, cloud services plus HA architecture means that we can really get to much higher levels of availability with zero or no downtime. So, this is great. We've got a strategy for ensuring that, we don't have any pets that we have to keep alive 24/7. If we can lose individual cattle at any time and it's not going to have an impact to our system, great. That's fantastic. The trick is, programming those load balancers and keeping them up to date as you're scaling out and dealing with all of these things is non-trivial. And this is a large part of what Kubernetes was built to deal with, is that Kubernetes has a lot of facilities in it to help maintain these HA systems. So I think, again, it's good to understand, like, what do we mean when we talk about availability? How do we get to those numbers? And then, when we talk about HA, to sort of overcome some of the shortcomings or manual human intervention, what is the complexity that we're adding to the system to be able to deal with that? And then obviously, how does Kubernetes help us to deal with that? So with that, I want to start by talking about application availability in a Kubernetes cluster. So I think, the simplest thing to think about is in Kubernetes, you've got a deployment which represents, your application. In this case, you've got Nginx running. And you create a single deployment and you tell Kubernetes how many instances of that application or server you want to run as part of that deployment. And Kubernetes takes care of all the hard work there, right? So like, I can say, hey, I want to run 3 instances of Nginx. So you'll get 3 pods, one to represent each of those. And then Kubernetes also has built-in facilities to do liveness, readiness, and startup checks on those application instances as they come up and over the life of them, to ensure that if there's any failure detected by Kubernetes in your app, then Kubernetes will have the information and the systems to orchestrate around that to ensure that, the load balancers and other services that are relying on it aren't affected by the failure of an individual pod or application instance in that case, right? So, here in this example, we talk about the liveness probe, which I think is the most commonly leveraged probe in Kubernetes, but I think all three, liveness, readiness, and startup, are important. But in the liveness probe, we can look at this and, when I create this deployment in Kubernetes, it's going to, create my application instances, in this case, 3 instances of Nginx, and it's going to automatically perform an HTTP GET against all of the application instances that I'm managing on port 8080 on just the root path, right? So great. If that responds, it gets a 200, then everybody's happy, that it assumes that that application instance or that pod is healthy. And the nice thing is that, as you scale up, as you become more successful and you need more capacity, you can scale that deployment to add 10, 20, 30, 40, 50, 100, 1,000 pods. And Kubernetes is automatically doing all of that health checking against those pods for you to keep the state and status of those application instances up to date based on the liveness probe that you define. Now, I'll also talk a little bit about the differences between them here. So liveness checks or liveness probe is performed over the entire lifetime of the application instance. And if we dig into the details here, right, it's going to wait 3 seconds after the pod starts before it will do its first check. It will do that check every 3 seconds. It will wait 2 seconds for the connection to time out before it considers it failed. And then, the failure threshold is, hey, how many times do I need to fail this liveness probe before I consider that instance or that pod as failed and mark it as such. Now, the nice thing is if you fail your liveness probe, then not only does Kubernetes stop sending traffic to it so that nobody that's trying to access it is impacted, it'll also automatically restart that application instance for you to try to give it a chance to come back healthy. Now, we also have readiness probes here, and this is slightly different in that it behaves and operates exactly the same. The difference is that if it fails for some reason and it's a readiness probe, then Kubernetes will mark the pod as not ready, as it's indicated here. And that's the indication that it shouldn't try to send traffic to that pod anymore. But for readiness, it won't restart that pod or the container instance. Instead, what it's going to do is continue the readiness check in the hopes that at some point in time, that pod will be ready to receive traffic again. Maybe it's got an external dependency.
Sorry, could you say that again?
Maybe it's got an external dependency that's not available at that moment in time, or some other issue is going on, but it could become healthy on its own without having to be restarted. Now, lastly here, we have the startup check. Startup is the same thing as liveness. It's used specifically at the start of the application instance in the situation where there's some other thing that it needs to wait for that may take a much longer time before the application or instance is ready to start processing requests. So that is deployments in a nutshell there. And I think, the key thing here is how these liveness and readiness probes affect Kubernetes' view of those individual instances and prevents traffic from getting routed to them. And the service construct in Kubernetes is how it's actually implementing that on the back end, right? So, if I create a service for my Nginx that we're referring to here, when a client in Kubernetes tries to go talk to Nginx, it's not talking to the individual instances directly. It's talking to the service. And Kubernetes uses a feature called the kubeproxy that will configure IP tables routing and load balancing to determine, which instances of a given application are actually going to receive traffic when a client goes to make a request. And, when those readiness checks from earlier fail, what, the kubeproxy does is it says I've got 3 pods for this, but one of them is not ready. I will stop routing traffic to that pod. So this is kind of how the Kubernetes deployment and pods work in conjunction with the Kubernetes service construct to determine, which pods are going to be receiving traffic when it gets requests from clients in the cluster for that. So, this is kind of how these pieces and parts work in concert together to ensure the availability of your application or service. Versus when we look at a traditional load balancer, every time I go add a new application instance or scale out, I've got to go update the configuration of my load balancer to add or remove those new instances of my application. The nice thing is that also in Kubernetes, when you're updating an application or service, right, it's automatically orchestrating, draining traffic from those application instances and routing traffic to the ones that are healthy. And all of this is orchestrated as part of Kube when you're using these constructs, rather than you having to constantly go through and manually make all these updates to the configuration of your load balancers to ensure that you're sending traffic to the healthy instances of your app or service. So, really powerful constructs here. Again, I think, it's important to remember that Kubernetes is only as smart as you make it. So it's critical that you set up good liveness and readiness probes. Startup probes may not be needed for every service, but really those liveness probes and readiness probes are really critical to ensure that Kubernetes is routing traffic to your healthy application instances.
Jake, one of the guys, his name is Frank. He has a question. Can he
yeah, sure. Go ahead.
Frank, go ahead. Frank, go ahead. Do you see his question? Let me see.
Let's see if I can see it if I skip out of here.
His name is Frank,
I do not see any messages.
Okay, so one thing is that we can do, if anyone have a question, they just leave it in the text message, in the message box, then you just go back and look at the questions. You can go ahead.
Okay. All right. Play through the current slide. All right. So, let's continue talking about application availability a little bit. So, what happens when there are failures in a Kubernetes cluster? So the simplest failure that we'll talk about is a pod failure, right? So let's say, you've got, pods running on one worker node and they're talking through a service and kube proxy to talk to pods on another node. And hey, lo and behold, one of those pods dies, right? And it happens all the time. Listen, out of memory or some other failure in your application code causes a failure. That's why we're running an HA and we have multiple pods available. But what does Kubernetes deal with? How does the Kubernetes deal with this? Well, first, the good news is that, for cloud native applications that are built in an HA architecture, you really shouldn't have any downtime in these scenarios, right? Especially if your client is using retries, right? It won't take Kubernetes long to discover that that pod is no longer healthy through the liveness probe or readiness probe. And it will, quickly start routing traffic around those failed pods, and your client will start seeing successes in short order. Typically, this is the identification of a failed pod and updating the routing tables and IP tables to route around that can take, anywhere from, say, a few seconds, 2 to 3 seconds, up to 10 or 15 seconds. There's definitely a lot more detail available on some of the configuration parameters and stuff that you can adjust that'll determine what that latency is. At the end of this talk, I'll have a link to my book where I go into a lot more detail about what are those settings, how does it affect the recovery time, that sort of thing. So, if you're interested in finding out a little bit more detail about that or any of the topics that we'll go through, there's plenty more information available out there that goes into more detail about it. So yeah, that's pretty much, pod failures are very simple to deal with, right? This is really what Kubernetes was built to do, is to, deal with failures of individual application instances in these Kubernetes pods and routing traffic around it. Now, something else that can happen is an entire worker node in a Kubernetes cluster could fail, right? So Kubernetes has lots of worker nodes. They're all running different applications and services and things on them. If an entire worker node dies, we could have some slightly different results, right? In the end game is the good news that Kubernetes will absolutely deal with the failure of that node automatically. You don't have to do any work in order to recover from that. That's built into Kubernetes itself, is that one of these nodes fails. But I think it's worth talking about a little bit, like what's the flow of things that happens over time when we look at this. So obviously, like, hey, at T0, time zero, worker node fails. Great. For some period of time, initially, traffic is not getting rerouted. So pods could still be trying to send traffic to that worker node, and those requests are going to fail or time out. Now, in Kubernetes, there's this node lease duration. There's obviously, you can Google, there's plenty of information on it, but the important thing to note is that it's essentially the amount of time it takes Kubernetes to determine that a worker node may be offline, right? So essentially, each worker node has to go renew that lease on a regular interval. And if the node lease duration is, say, 20 seconds, if it doesn't renew that lease within 20 seconds, then Kubernetes will say, hey, this worker node is no longer available. That also means all the pods and services that were being served by that worker node are no longer available. And I'm going to go update the kube proxy instances in the entire Kubernetes fleet to stop routing traffic there. So really, that node lease duration plus that IP tables sync period is how long it takes kube proxy, the shortest amount of time it will take for it to go refresh that routing. And by that time, traffic is rerouted. So, again, depending on sort of the configuration and settings of the cluster, that node failure will be recovered and traffic will be rerouted within, say, 10 to 20 seconds max. And again, right, no work is required by an administrator. This is all going to be handled on its own. And in fact, after the pod eviction timeout time is reached, right? Like, let's say that worker node stays down till that eviction time is reached, then Kubernetes will actually automatically reschedule or recreate all the pods that were running on that worker node on some other healthy node to recover any loss capacity that you would have had from that worker node being down. So, these are really powerful constructs within Kubernetes that, again, for operations teams, makes it super easy to be able to deal with pod failures, worker node failures. All of these things can be dealt with by Kubernetes without any intervention from, an operator or SRE team. So there's one other kind of data plane failure that can happen that Kubernetes can deal with, which is a complete zone failure. So, in modern cloud architectures, we often talk about multi-zone configurations where we have workload running in 3 separate zones. And a zone is really kind of like any, the isolation can be any level of isolation that provides resiliency between different sets of infrastructure. When we think about, modern cloud, whether that be, IBM cloud or AWS, Google, Azure, any of those, they all have these zone concepts baked into their cloud platforms. So as long as you're distributing your workload across those zones, then, zone typically in the cloud sense means separate power, separate networking, usually separate physical building. So, anything could happen to that zone in a metro area, and it's not going to impact the other zones. Kubernetes can deal with that entire zone failure, just like it can deal with an individual node failure as well. So, the recovery process is largely the same as we talked about with a node failure. There's a couple of notes here that I'm not going to go into great detail, but essentially, there's this unhealthy zone threshold that Kubernetes can use where if it sees lots of failures of nodes in the same that are marked from the same zone, then it deals with the recovery in a slightly different fashion. And really, this is just to prevent Kubernetes from thrashing, uncontrollably when there's a lot of failures that happen at the same time because all of the worker nodes in one zone fail. And the large cluster threshold and the node eviction rate basically are used to sort of help Kubernetes make decisions about like how quickly to try to do the pod recoveries, et cetera. But the same holds true as a single worker node failure where it's going to rapidly start rerouting traffic around that failed, all the workers in that failed zone so that you can maintain availability of applications and services there. All right. So those are some of the data plane failures, and these are great, right? Because Kubernetes deals with these all automatically. There's no real additional work required by the user beyond just ensuring that their application is, cloud native and highly available.
Jake, one quick question. Is it possible, is in any scenario, these failures happen at the same time? Like, if that happened, then is Kubernetes gonna prioritize or sequence them? How's that like?
Do you mean like two zones fail at the same
No,
time?
no, like zone and then the like. Do you remember the previous slide that you have like pod? Like,
Yeah. So, yeah, I mean, I think something that's probably fairly common is like multiple nodes or nodes and pods can die at the same time. It doesn't really do any prioritization. Essentially, it's going to start the traffic rerouting immediately across the entire fleet. It's not doing any prioritization there. When it gets to the point in time where it's going to start rescheduling failed pods, either individual pods from one worker node or a whole zone's worth, or a whole worker node's worth of pods. Kubernetes does have a whole system of setting up prioritization of individual pods, and it will use that weighting system to determine which pod should it try to recover first. So let's say, a whole zone fails and there's 100 pods running in that zone. All the pods in that zone will have a priority associated with them. And it will start rescheduling the highest priority pods first. So, I mean, it does, the pod owners or developers can provide some indication as to like what the priority of their workload is, and that is basically a hint to Kubernetes to determine which pods should it try to restart first.
and then also, if there is a priority for zone too, right? Like if there are multiple zones, you can prioritize zones.
Yep, you can, right. So like in a multi-zone configuration, when pods are being scheduled, there's tools in Kubernetes to set affinity or anti-affinity, which, if we look at, a scenario where we're running 3 pods in a deployment, we can set up zone anti-affinity to say like, hey, I want Kubernetes, I want you to ensure that you don't run, that each one of these pods runs in a separate zone. And that's part of the zone failure, capability, which is like, hey, if you ensured that your 3 pods are always in separate zones, when a zone fails, you can always guarantee like I'm going to have 2 pods still up and healthy in the remaining zone. So yes, that's part of the.
That makes sense. Yeah, that makes sense. Thanks.
Sure. All right. So let's take some time to talk a little bit about cluster availability as well. And so this is less about the actual workload that's running on the cluster and more about the cluster itself and how availability is dealt with there. So, in this case, my entire Kubernetes control plane here at the top of that's actually running the cluster is completely failed for some reason, right? It could be because etcd, which is the backing key value store for Kubernetes, has failed for some reason. It could be all the infrastructure is down. It could be that, I'm going through some update process. There's any number of things that could result in a total failure of the control plane. And one of the interesting characteristics of Kubernetes is that when that control plane has a total failure, all of the workload that is running on those worker nodes is not affected immediately, right? Everything that's running on the worker nodes continues to run exactly as it was. There's zero impact from that. Now, it's not, you do lose some capability. So obviously, if the control plane is down, you can't go to schedule new workloads onto those worker nodes. You can't scale it. Also, if there are failures on the data plane side, right? If one of the worker nodes fails or pod fails, there's no control plane to make a decision about how to restart or recover from that. So obviously, you don't want to run in a state of control plane failure for an extended period of time. But, short interruptions when there's no data plane or worker node failure that goes with it means, no issue or no failures of your applications or services during that time period. So, a nice feature, in some of the early days of Kubernetes, oftentimes this was how teams would do updates, is they would take down the whole control plane, they would do their update process and then bring it back up. They're just sort of working in that reduced functionality state while the control plane is down. Now, I think something else that's worth noting is that, look, if just one component fails in that Kubernetes control plane, there's no impact there either, right? As long as you're running an HA control plane. So, Kubernetes sort of, practices what it preaches as far as, proper cloud native architecture and things like that. So, the good news is that, if one of your Kube API servers or controller manager or etcd pods or something fails, that's not going to impact the functionality of the cluster in any way, shape, or form. All right. So let's talk a little bit about north-south network failure. This is, so, earlier we were talking a little bit about routing of data and traffic within the cluster, but obviously one of the things that we want to do with Kubernetes is build applications and services that we want to make exposed to the internet or to our corporate networks or whatever for others, other things outside of the cluster to consume. It could be a web app, could be, APIs, whatever it is. Kubernetes uses, external load balancers as a means to get traffic from out of the cluster to into the cluster. And typically we refer to this traffic flowing from outside the cluster into the cluster as north-south network traffic. And when we experience a failure there, the nice thing is that Kubernetes also has great integration with a number of, load balancers that are available, whether that be, an on-prem thing like an F5 or big IP load balancer, something like that, or if you're using cloud load balancers from, AWS, Google, IBM, Azure, whoever it may be, then Kubernetes also has functionality baked into it so that if it detects failures in the infrastructure side of things, it can automatically update those external load balancers to stop routing traffic to the components that are failing in the cluster. It also sets up health checking automatically in those external load balancers as nodes and pods come and go, so that it can automatically deal with failures that may be occurring in that north-south traffic. Now, this is all fine and dandy if there's just a single failure in that north-south traffic, right? Now, clearly, if the external networking device, the load balancer, can't get to any of the worker nodes or any of the pods that are in the cluster, then you will totally have a complete failure for traffic reaching your services that are running in the cluster. But again, like we're shooting for bend but don't break and resiliency here, and so when we get into these scenarios where there's a single failure, there's no problem there, right? Kubernetes is taking care of that for you instead of you having to constantly keep those external load balancers up to date to deal with those failures.
I think one quick question is that if you have DNS load balancer, does Kubernetes also sync with DNS load balancers?
It is possible to do that. Yeah, there are some load balancing implementations that do know how to do DNS updates. Or if you're using like a GSLB from like Akamai or Cloudflare or something like that, and it's programmed with health checking by the Kubernetes load balancer extension, then yes, it can also apply for DNS load balancing.
Thanks.
Yep. All right. Now, let's talk about east-west total network failure. This is pretty similar to earlier when we talked about zone failure. The only difference here is that not only did like the worker nodes fail in zone C, right? But this is more about the network failure between zones A and B and zone C. Now, this is something I call it a clean failure, right? Where zone C is segmented from zone A and zone B, but zone A and B can talk to each other no problem. So Kubernetes will totally deal with this failure, no problem. All the systems in your Kubernetes cluster will recover normally without any intervention from an operator. And it's able to do this because, zones, the control plane in A and B are aware of the fact that the worker nodes in zone C are failing. And so they will stop, they'll route traffic around zone C. And the control plane component in zone C is also self-aware enough to realize like, hey, I can't establish quorum with my buddies in zones A and B, so I am not going to continue to try and run any workload or make any changes or do any work, even if I'm getting API requests into zone C. So, this is something that Kubernetes deals with pretty gracefully, and again, doesn't really require any special intervention, on an operations team standpoint. Now, there are all kinds of failures that could potentially happen that might not be automatically dealt with by Kubernetes. And, one that I think it's not common, but can happen, and I've definitely seen personally in the past, is this. There is the control plane is totally healthy, and the worker nodes themselves are healthy, but for some reason, worker nodes in one zone can't communicate with worker nodes in another zone. And this is really common because a lot of times in production systems, right, the control plane for a Kubernetes cluster is running on networks that are isolated separately from the worker node networks. And, this could be like human error or a switch failure, or anything could happen that causes this network segmentation between the zones on the data plane only. And the reason why this causes problems is that like, when there are failures in a Kubernetes cluster, the only way Kube knows to detect that is if the control plane can detect that thing has failed, or something in one of the worker nodes is telling the control plane, hey, something's not healthy, you should deal with my pod failing or whatever. But in this case, the worker nodes in zone C think everything is just fine, and the control plane thinks that everything in zone C is just fine because it doesn't have visibility to that connectivity between the worker nodes. And so, it's going to keep trying to send traffic between all the worker nodes and all the zones. But anytime a request tries to go between zone C and one of the other zones, it's going to fail. And it doesn't have any way to do retries there. It doesn't have any way to recover from that. Kubernetes cannot detect this today. And, I think it's sort of like a known limitation of Kubernetes. A lot of operations teams will set up their own health checking for intra-zone networking or other capabilities to detect these kinds of failures. And they can have, all kinds of automation that they set up to deal with that. One of the, easiest things is that like, hey, if you detect this network segmentation on the data plane side, is in Kubernetes, you can, as an operator, just mark all of the worker nodes in zone C as not healthy, and then Kubernetes will do all of its traffic routing to stop sending traffic there. But the trick is that Kube can't detect that. It's really up to the operations team to do that detection. And it's, common practice, I think, to set up that detection and to automate the marking of nodes as not healthy in a segmented zone. Now, there are some tools that can kind of make Kubernetes more resilient to these kinds of failures. Service mesh solutions like Linkerd or Istio, or the new alpha feature in Kubernetes 121, known as topology-aware hints, can kind of help you cope with this. Essentially, oftentimes this is called like zone-aware routing, where when traffic, when a request leaves one pod and is destined for another service in the cluster, it will try to go connect to an endpoint that's in the same zone as the request came from as the first priority. And so if you have that enabled, then, hey, if traffic is coming from a service in zone C and going to a service in zone Z, then it won't experience any failures, right? The in-zone networking is fine. And so if you've got that set up, then you may not ever even experience failures, until there are some other failure layered on top of that that's preventing it from being able to service the request within the same zone. So that's some pretty new technology. I think it's worth reading up on if you're interested. And some of the service mesh solutions have had this zone-aware routing for a while. But it's just something worth noting that, there are tools out there that can help you to sort of cope with some of these, more advanced failures that you can experience in Kubernetes. All right. So that is it. Hopefully, that gives everybody some good tools and some ideas about like how to go deal with availability for applications and Kubernetes clusters. Like I said, there's a lot to discover out there. This is just sort of kind of like the tip of the iceberg, but it gives you some introduction into the types of failures you can see, and how Kubernetes is able to kind of deal with some of these things. I will say a couple of quick plugs, and after this, I'll definitely happy to handle any questions. So first, if you have any follow-on questions, you can reach out to me via email or on Twitter. Very active there and always respond to DMs. My DMs are open, so you can always send requests on Twitter. There's a link here to our book, Hybrid Cloud Apps with OpenShift and Kubernetes. The content that I reviewed here today is based off of one of the chapters in that book, and we'll go into like way more detail there. So if you're interested in learning more about today's topic, you can certainly dig into the book and learn a lot more of the details and some of the content that I covered today. And then my final plug is that I am hiring at Fidelity now. So